we are looking at arriving at a term for the optimization of evidence lower bound for DDPMs. We saw that the final objective for DDPM had three terms. One was the reconstruction term, the other was the KL term, the prior matching term, and the third term which we called as the consistency term. So, we saw that the prior matching term is independent of the model parameters theta, so we just ignored that. The first term is the reconstruction term, we will revisit that in a while. We were simplifying the consistency term, also known as the denoising matching term. So, we saw that the consistency term or the denoising matching term consisted of a KL divergence between two distributions, Q xt minus 1 conditioned on xt and x naught, which we called as the true reverse distribution, and p theta of xt minus 1 given xt, which is the modeled reverse distribution. We wanted to minimize, or rather we wanted to compute the KL divergence between these two distributions. Now, we do not have access to q of xt minus 1 given xt and x naught. Therefore, we used Bayes rule to find out q of xt minus 1 given xt and x naught. After some algebra, we showed that this particular distribution q of xt minus 1 given xt and x naught happens to be a Gaussian distribution with a certain mean which we called as mu q and a variance which we called as sigma q, where mu q was given by a linear combination of xt and x naught. Note that xt and x naught are vectors and all these alphas here and the derivatives of it are all scalars. So, this is nothing but a linear combination of xt and x naught, and we saw that sigma q is nothing but a diagonally scaled version of the identity matrix, where the scale is given by small sigma q squared. So, q of xt minus 1 given xt and x naught happens to be a normal distribution with certain mean and variance. We also know that the model distribution or the reverse or the backward distribution for a DDPM is also assumed to be a Gaussian distribution because it is a Markov chain with Gaussian transitions, and we call the mean as mu theta, and the variance is assumed to be the same as that of q of xt minus 1 given xt and x naught. Now, one can also parameterize this variance and estimate it, but in practice variance is kept as a constant. Now, it has been observed that only by estimating the mean for every transition you get considerably good results, and the variance can be kept as a constant. So, this is kept as a constant and it is taken to be the same as that of the distribution q of xt minus 1 given xt and x naught. Okay. Then what happens is, finally the consistency term happens to be the KL divergence between these two Gaussian distributions. One Gaussian distribution has mean mu q and variance sigma q, the other Gaussian distribution has mean xt minus 1, the variance mean as mu theta and variance as sigma q. Okay. Now, with this let us continue from here. So, this KL divergence between two Gaussian distributions can be deterministically computed, as we have seen multiple times, and it is given by this particular expression. It's log of sigma q, the determinant of sigma q, divided by, note that the variance of both of these distributions are same. So, this will be log of determinant of sigma q by sigma q minus d, where d is the data dimensionality, and we have trace of sigma q inverse times sigma q. This would have been the trace of variance of the product matrix products of these two matrices, but in this case they are both the same, plus the quadratic form of the difference between the means of these two, which is mu q minus mu theta minus mu q transpose sigma q inverse times mu q minus mu theta. Please note that this mu q and mu theta, both of them are d-dimensional vectors because they are the means of a d-dimensional Gaussian distribution. So, this would be the KL divergence. So, this would cancel out to be 0, and trace of this will be identity, which means that this would be d. So, this and these would cancel, and we know that sigma q inverse is simply So this is equal to, we know that this is sigma q squared times the identity inverse. This is what we have. So putting all these together, we will have this to be equal to half into mu theta minus mu q, the norm of this. So for all those complicated looking equations, so there will be 2 sigma q squared here as a constant, or 2 sigma q squared times this. So now for all the complicated algebra that we did, the final ELBO looks very elegant. So this is simply a regression. This is a regression over mu q, right? So this is the mean squared error cost, or squared error cost. There is no mean yet here. So this is the squared error cost, and what we are doing is we are trying to match mu theta to mu q at every time step t. That is all it is, right? So finally the ELBO turns out to be having the following form. So we will have to combine the first term, which is the reconstruction term as well. So the final equation for ELBO in DDPM looks the following. So ELBO for DDPM. So we called it j theta of q. This looks like, so we had an expectation of log of p theta x naught given x1. So this was the first reconstruction term that we had, and this was with respect to q of x1 given x naught. So we had derived this, plus the second KL term, right? The prior matching term will vanish because it is independent of theta. So we had this to be t equal to 2 to capital T, expectation of 1 by 2 sigma q squared times mu theta minus mu q squared, and this expectation is again with respect to q of xt given x naught. Let me, if there is an expectation with respect to q of xt given x naught, and this here minus sigma t equal to 2 to capital T. So that's it. So this is the final ELBO that we need to optimize. So now we have where xt comes from normal 0 1. So because this is the stationary distribution of the forward Markov chain that we have. So this is the final expression for the evidence lower bound for a DDPM. So this is what we are going to optimize in all the practical implementations, but we will simplify this a little further to have different kinds of forms that are easy to be implemented, but fundamentally this is the expression that we are going to optimize. Okay, let us try to simplify this further. There are multiple forms for this ELBO. Okay, so we will look at different kinds of expressions of this ELBO and see how this can be estimated in practice. Okay, how this can be optimized in practice. So this is q of xt given x naught. Great. Okay, so now let us first construct. So to compute the reconstruction term, let us first compute the reconstruction term. So let us compute the reconstruction term. So what is the reconstruction term? So consider, so we will look at the expectation later. So consider log of p theta x naught given x1. So this is the first term that we have, right? So where x1 is the first latent vector that we have, or the first noisy version of x naught. So what is this equal to? We know from the model the definition, p theta of x t minus 1 given x t. So this is for any t. We know that this is a Gaussian distribution, right? This is the model assumption that we have made, with the mean equal to mu theta and the variance is equal to sigma q, right? So this is the definition that we have for anything, which means that for p theta of x naught given x1, just have to plug in the appropriate equation. So this will be equal to a Gaussian distribution at x naught of x naught, with the mean being equal to mu theta of x1, right? So this is in general, see, mu theta is a function of xt, right? That is how we have constructed it. This is a function of xt, and we have sigma q here. This is mu theta of x1 here, and this is sigma q square times identity, because that is what we have made our variance to be equal to, right? So which implies log of p theta of x naught given x1, which is the term that comes up in the reconstruction term, is equal to log of, so we have 1 by 2 pi sigma q squared to the power of d over 2. So this is the expression for a d-dimensional Gaussian. So we have e power minus x naught minus mu theta of x1 squared divided by 2 sigma q squared. This is the usual definition of a Gaussian distribution, right? A d-dimensional Gaussian distribution. You can just take this and just simplifying, take the log and the exponentiation out. If we do this, this will be simply equal to minus x naught minus mu theta of x1 squared divided by 2 sigma q squared minus d over 2 log of 2 pi sigma q squared. Now this term is independent of theta, and this simply can be ignored. Okay, this is because this is independent of theta. When we are optimizing with respect to theta, we can just take that out, right? Okay, so now with an expression for this, now we have to see how to optimize for the ELBO that we have obtained. So how do we do it in practice is the question. Let us do that. Okay. So which means the reconstruction term, which is log of p theta of x naught given x1, simply equal to minus or I'll write it as proportional to, because I am taking out the constant term. So mu theta of x1 divided by 2 sigma q square. That's it. Okay. Now the final ELBO, which is j theta of q, is equal to this particular term. Let me write that down. So this is the second term that we have. We'll keep it that way. Perhaps I'll write it down. So this is equal to, we have an expectation of minus x naught minus mu theta of x1 squared. This is with respect to q of x1 given x naught, x1 given x naught. Okay, this is the first term, and we have plus minus expectation of some t equal to 2 to capital T expectation is a linear operator, I can write it inside, but anyway. So this is minus expectation is with respect to q of xt given x naught. The term that we have here is 1 by 2 sigma q squared times mu theta of xt minus mu q whole squared. So, this is the final term that we would want to optimize. Okay, this is what we need to optimize. So, what do we need to do? We need to find a theta star that would maximize. So, remember that all we are doing is maximizing the lower bound on the evidence, which is minimizing the KL divergence between Px and P theta. So, our objective has not changed. So, this with respect to theta, we need to optimize this, right. This is what we need to do. Now, what are the unknown parameters here? Of course, we know what mu q is. Mu theta is something that we do not know. Now, if we have something that we do not know, what do? We simply estimate that using some function approximator, which is the neural network. Okay. Now, the basic idea here, so basic idea is to express the unknown which is mu theta of xt using a neural network, using a function approximator which is neural network, right, using a function approximator which is a neural network. Okay. Now, how do we do that? So, let us say that there exists a neural network . There exists a neural network. There is a particular reason why the architecture is this way. I will describe that as we move on. So, here is a neural network. So, this neural network takes xt as an input. Let us call this the theta network, and what this gives at the output is mu theta of xt, right. I mean, this neural network is a regressor on mu q. It is a regressor on mu q because the loss function here is mu theta minus mu q squared. So, that's the loss function that we are trying to optimize. So, this neural network takes an xt and predicts what mu theta is. That is all we need. So, if we have a neural network that does this sort of a thing, then we are done. Okay, that is what we need. However, I mean, in principle, this is all that is happening in a DDPM, okay, or a diffusion model while training a diffusion model, but there are a few improvisations that are done on top of this, which we will see now. So, basically the idea is to express the unknown quantity, which is mu theta of xt, using a neural network. So, why this particular shape of neural network? That is an implementation detail. See, xt and mu theta are both of same dimensionality, right. When xt also lies in Rd, mu theta also lies in Rd. Therefore, whenever you are trying to solve a regression problem, the usual convention is to use an architecture this way. This is also called a U-net architecture, where the dimensionality of the neural network keeps decreasing up to a level, okay, and there will be a bottleneck layer, and from there the dimensionality will keep increasing. So, basically the dimensionality here decreases up to a certain level. So, this is so decrease the dimensionality, and from here the dimensionality is increased the dimensionality so that you get back to D. So, this is the typical architecture that is used in a DDPM. Okay. So, because as I said, when you are regressing over a variable that has the same dimension as the input, it has been found out empirically that these sort of architectures help well. Okay. As I said, there is no theoretical underpinning so as to why one should resort to U-net sort of architecture, but this is the standard practice that is used. But more, I mean, details on this will be discussed during the tutorials, the implementation tutorials. But what is of importance for us right now is that the ELBO has something that is unknown, which is mu theta, and we approximate this using a neural network. Now, one might ask a question, right? So, mu theta depends on xt, right? So, every xt has a different mu theta. Now, why are we having one neural network to estimate all the mu theta? Again, that is a design choice. The reason we choose one mu theta for all time steps t is to ensure that there are sharing of parameters, parameter sharing across different neural networks that regresses over mu theta or predicts mu theta at every xt. So think of it like having different neural networks with all shared parameters. So it's like having one neural network that predicts mu theta of xt for all given xt. So there is only one neural network that takes any xt and predicts mu theta also, mu theta for that particular xt. There is another important detail that is to be studied here is that this neural network does not have a sense of time, in the sense that this neural network has no understanding of what this particular xt correspond to in terms of time. See, recall that this xt is the tth latent vector starting from x0, but this neural network does not have any idea about the time. Okay. So typically what is done to counter that is t, which is the scalar time parameter, also is given as an additional input to this neural network. Okay. Now how is and t here is a scalar, right, because it is from 0 to capital T, which is a hyperparameter. So how is this t given as an input to a neural network, to this particular neural network, is a question. Okay. So let us write that down. So there is one neural network which predicts or regresses, predicts mu theta of xt for any xt. Okay. The other detail is to ensure that neural network has an idea of time, time rather an idea of time, another variable corresponding to another fixed variable corresponding to time is also given as an input, variable t, okay, corresponding to the time, corresponding to the time of xt is given as input. Okay. Now t, as I said, the time variable is a scalar, xt is a very high dimensional vector which is in d dimensions. How does t or a scalar given as an input in addition to xt? So typical way that is done is t is converted into a vector using sinusoidal positional embeddings. What is this idea? The idea is that you are given some time vectors, some scalars, right, from 1 to capital T. Now you need to convert all of them into a vector, because why is that needed? That is needed because typically what happens is, if you take a data vector that is in very high dimensions d, and if you just concatenate a scalar into that, oftentimes that scalar gets completely ignored by the neural network. So a better practice is to convert this scalar into another vector, typically of dimensions of this data, and then concatenate or add and give it as an additional input. Now the question is, t is a fixed scalar variable and we need to convert that into a vector. So how is that done? That is done by using a function called positional embedding. Basically, so positional embedding is simply a function p that takes t and produces a vector t cap. Okay. So now t, as we know, is a scalar which is a positive integer. Yeah, it is a positive integer, where t cap is a vector, a real valued vector in d dimension. So, it converts a scalar which is a positive integer into a d dimensional vector. How is that done? That is done using a particular, I mean there are multiple ways to do this. Now, in the particular case called sinusoidal embedding, so what is done is, so we have t cap evaluated at a particular t is given by a vector. So, this vector is in d dimensions. This is a 1 cross d dimensional vector, because that is what we are looking for. This is given by a particular expression that is derived using the harmonics of sines and cosines. Okay, so that is the idea. Let me just write that down. So, this is also called the sinusoidal positional embedding. In fact, this is the same positional embedding that would be used in a transformer as well. So, we will look at this when we look at the transformer as well. So, it is given by sine of WKT, the ith, okay, let me write it as the ith row of this is given by sine of WKT if I is equal to 2k. If it's even, then it is, if it's odd, then it is given by the cosine of WKT if the position is odd. Okay, where WK is 1 over what's the length? It is 10,000 to the power of 2k by t. Which is a constant number. So, basically what this is doing is, it is converting, so once we do this, we get a vector t cap corresponding to every t that is of dimensions d. Okay. So, we get a vector that is of dimensions d for every scalar. Okay. So, now you take that particular, so this, I mean think of it like just representing this time scalar in terms of a vector which is of dimensions d. You can just take that vector as an input and give it as an input to this particular network that is regressing over mu theta. So, that is the basic idea of using the positional embeddings. We will get to positional embeddings again when we look at the transformers in the context of large language models. Anyway, so let us get back. So, what we are actually doing is representing this mu theta of xt, which is unknown, in terms of a neural network which takes xt as an input and regresses over mu theta. Okay. So, we also have this another term in the ELBO, okay, which has x naught which is regressing over mu theta of x1 and x naught. So, all we need to do is that whenever we take x naught, which is an input sample, we need to pass it through this particular network. Whatever we get is mu theta of x1. Okay, we need to start with x1, take x1 and pass it through this neural network, get mu theta of x1 and try to just regress it over x0. That's all. So, that is the first term. The second term is that we take multiple t's, we sample a batch of t's, and for all those t's we compute what mu q is. Remember, mu q is also a function of xt and x0. So, we compute mu q for that corresponding xt, and then we pass that xt to through the neural network and compute take the output and regress it over mu q. So that is the broad training procedure of how it is done. I'll walk through the training again, but that's the broad training procedure. This should maximize the ELBO, and this is all the training procedure is, okay. But there are multiple equivalent interpretations of this. This will work in practice, okay, but there are multiple equivalent interpretations of this which we will see now. Okay. So let us look at equivalent interpretations of the ELBO.